Okay, we saved the best for last, keynote-wise. And so this was, I usually save a spot, you know, when I'm planning an event for an unexpected person to come in and, you know, really round out the panel. And I saved a time slot here at the end. And one of the engineering professors, you know, here at Fulton, who's sitting right here in the front, had reached out and asked about, is there any open space? And I had said, yeah, there definitely is. And I didn't know who he was talking about, but our final keynote, he's the founder and chief executive officer of Blue Planet Systems Corporation, a serial entrepreneur with expertise in biomineralization. Over the past 25 years, Dr. Constantz, as founder and CEO, led 3 medical device companies to advance mineralization technologies for orthopedic bone cements. Dr. Constantz founded Calera to address global climate concerns with aspirations to permanently sequester gigaton quantities of carbon dioxide in the form of carbonate minerals. Blue Planet is the next generation product using carbonate materials. He received his doctorate in earth sciences at the University of California, Santa Cruz in 1986, and studied biomineralization as a Fulbright scholar at the Weizmann Institute of Science. And I am proud and honored to have Brent Constantz as our final keynote of the day. So Brent, you want to take us home?
I'm going to tell you about what we've been doing for about the last decade in this area. Blue Planet was founded to have a sustainable solution to mitigate gigaton levels of CO2. And by sustainable, we don't just mean technologically sustainable, we mean sustainable, economically sustainable, societal sustainable, not just something that has the potential to work if all the technology worked. Everything else has to work too. I like to remind everybody, where is all the carbon? Because you know, if you ask an audience, where is the carbon? We don't actually fully appreciate, a lot of folks. If you look at where the carbon is, there's about 800 billion tons in Earth's atmosphere. There's about 2,400 billion tons in the whole biosphere, meaning all the rainforests and plankton in the ocean and everything. There's almost 40,000 billion tons in the whole hydrosphere, the oceans, ice caps, rivers, lakes. But in the lithosphere, mainly as limestone, there's over 100 million billion tons. So over 99% of all the carbon associated with Earth is actually sitting in limestone in the lithosphere. And that gives you this huge leverage on a huge reservoir. Just a fraction of a percent of a change in the amount of lithified mineralized carbon can have a tremendous effect in the net sequestration of carbon. These are all different taxonomic groups that mineralize calcium carbonate skeletons. And almost all this 100 million billion tons of rock that's in the lithosphere, that's mostly limestone, is a result of biomineralization over time. So over 99% of all the carbon on Earth gets cycled through this process of biomineralization at some point. So you could argue it's probably one of the most important fundamental processes in thinking about global carbon that there is. The other thing about all that limestone, though, is that there's about 55 billion tons of rock mined every year globally. And it's not just mined, it's mined, processed, moved, and used and paid for all over the world. In the poorest countries, in the richest countries, they're building roads. And frankly, the poorer the country, the more government generally has control of infrastructure spending. So it puts this huge procurement power, even in the poorest country in the world, to mitigate billions of tons of carbon and only spending money they were already spending on infrastructure anyway. So it's something we've determined is really one of the real key tools. And I should say that I've founded other companies that made cement. And I'll explain why. But we think by making the limestone rock, we can actually get processes in place around the world that can mitigate huge, huge amounts of CO2 profitably, economically, in a sustainable way, even in poor countries without subsidies. And anything that's going to be sustainable is going to have a big circular component integrated into it. And what we do is we take feedstock that I'll show you that contains calcium and CO2, and we make limestone directly, and then we use that limestone as the aggregate in concrete, which is the most used building material in the world. And it's ubiquitous everywhere. So fundamentally, what we're doing is different than everything you hear about in the IRA Act, where what you see is what's being subsidized, for example, by the government is to capture CO2, put a lot of energy in it to purify it, to turn it into a liquid, to build pipelines, to move it, then inject it underground where it's going to form carbonate minerals permanently under the ground. And there's a new legislation, it's called 45Q, that was approved by Washington, that's going to pay people, I think, $90 a ton for doing that. And there's whole businesses, mainly out of the oil industry, that are springing up to take advantage of that tax credit. We don't do anything like that at all. What we do is just in one step, we do what happens to that 100 million billion tons of carbon already, which is we form carbonate, CO3, which is a spontaneous reaction. And then we go directly to limestone, which is what happens. That's what all the organisms that do biomineralization do. So we use a fraction of the energy to manage the carbon versus what is the most common method of carbon mitigation. So when you hear about a direct air capture company that's selling voluntary credits for carbon they plan to capture in 10 years, they're talking about this route where they're either capturing it from the atmosphere or from a power plant, turning it to a liquid so they can inject it and then underground and get a subsidy for doing that. So if you look at the different sectors, you know, we know the IEA has charted out a course to lower, you know, everything from power to industrial to transportation over a course over the next few years to get out to 2050 when we're net carbon neutral. And major players, major CO2 emitters all over the world are signing different pledges about lowering their CO2. And that's where you really need to get to, is the people that are putting out the CO2. It's not small players. You know, one company can put out tens of millions of tons of CO2. And so that's really where you want to go to address, you know, the real issues. Cement, for example, in the industrial sector puts out quite a bit, about 2 billion tons of CO2 every year. And it costs them a lot of money, so they have very little incentive to, or it's harder for them to argue to spend money on mitigating CO2 coming out of their sector. But all these sectors are putting out enormous amounts of CO2. About, we think, 30-something gigatons. So here's basically what we're talking about doing, is taking CO2 from buildings, tailpipes, electricity and heating, industry, putting it through the process, and making 55 gigatons of limestone, and basically replacing all the mined limestone, so replacing open pit quarries with what we call urban quarries, and making the rock where the CO2 is being emitted from the raw materials that we have there. And I'll explain that a little more in a second. But what's important is there's already 55 gigatons being bought, purchased, and moved today, and most of it's limestone. So we're not really changing things up very much. Instead of mining it in British Columbia and barging it down to Los Angeles, we're going to form it right in Los Angeles. Now, when people think about concrete, which is where we're going to store this limestone in the concrete, concrete is cement. It's like 10 or 15% cement, and it's about 70 or 80% sand and gravel. And we're making the sand and gravel component, so we're making the largest component. Now, what most of us have done, and I've founded a company that did this, is work on the cement component. And the reason is that if you look at where this embodied CO2 in concrete is, it's not in the aggregate, it's not in the sand and gravel, because that was just mined and moved. It's in the Portland cement, which is the binding phase. So it's responsible for 96% or more of the carbon footprint of concrete. So it makes sense to dive in and try and get rid of the carbon footprint of Portland cement. But if you look at the volume, most of the volume of concrete, the most used building material, is actually the sand and the gravel. So if you really want to store a lot of CO2 somewhere, you're doing much better with that, the sand and gravel component. Now, something I don't want to skip over is the molecular weight of calcium carbonate, which is what limestone is 100 grams per mole. And the molecular weight of CO2 is 44 grams per mole. So if I have a ton of limestone that we've made via this process, I have 440 kilograms of CO2 that's now permanently sequestered in the crystalline state. So of this 760 kilograms, 40% of that is CO2 that's been captured and mineralized, which goes way beyond any sort of potential of any carbon captured material that you can find. And if you look at the concrete industry's current approach to address their problem, and they're putting out 2 or 3 billion tons of CO2 a year, and they're trying to address it with energy efficiency measures, burning tires, putting a substitute in for the cement. They're recognizing they need at least another 1 billion tons of new technology and changing buildings to get to their goal for 2050, which is 700 million tons. And the governments are doing a lot of interesting things. There's a lot of new policies coming through in building regulations, certifications, to encourage people to use lower carbon concretes, because in most buildings, concrete is the big player in terms of the carbon footprint of any building. And if you look at aggregate, for example, the United States is mining quite a bit of aggregate, as are all countries. So there's an existing market for the aggregate. So what we're planning to do is, if this is the CO2 and this is the amount of aggregate, in the market. By 2030, we're planning to be able to capture 200 megatons of CO2 a year. By 2050, over 5 billion tons of CO2 a year is our current goal. Well, that 5 billion tons of CO2 will make 12 billion tons of limestone because of the difference in the molecular weight. And that's where we're focused right now, and that's our plan. Now, there's a large number of folks interested in this problem, in both the removal of CO2, but also making the built environment less carbon intensive, and even carbon negative in our case. So people are working on the aggregates, and that would be us. We're working in this area, making synthetic aggregates. People are working in new cements. There's a whole plethora of companies trying to replace cement. The problem with replacing cement, and I've done this before, I built a whole factory and repaved Highway 1 in California with a new cement. Cement is highly regulated because it's always curing. And practitioners want to see a decade, 2 decades of experience before they're going to implement anything. That's not true with aggregate. Aggregate is just rock and sand that is static. There are a number of companies trying to make things to supplement cement, but not the cement itself. And then there's some other companies that are buying that purified, liquefied CO2 that was going to get injected into the ground and fumigating wet concrete with it, and which sounds like a fantastic idea. Unfortunately, less than 1% of it actually gets in the cement, and most of it just blows off into the atmosphere. One of the biggest problems, and it sounds like the people in this room probably are aware of it, is there are a lot of claims about how green something is or what a great thing for the environment it is, and most of the time they don't always hold up to their claims. And so there's a new system that's been put in place. It was published by the Canadian Standard Association, who monitors a lot of the ISO standards for carbon sequestration and that kind of thing, called the Carbon Star Rating, which is now a US-Canadian bilateral standard, and it's going to a global standard. But what it does is it tells you the carbon footprint of a yard of concrete. So, for example, we're working with LinkedIn out in Silicon Valley, and they're building a 200,000 square foot campus, and they have to make it carbon neutral, which is impossible given all the steel and concrete and all that. What they did was really smart. They brought us in, and then they brought 2 internationally renowned architectural firms. And they said, look, we have to build this building carbon neutral. So how much concrete can we have? How much steel can we have? How much glazing can we have? So they designed the building based on the carbon footprint that would result from the materials they were using before they designed the building, which I thought was really smart. But now they have a new lever. They were to say, okay, the regular concrete is 385 kilograms per cubic meter. You know, if we use that and the steel, we're never going to get to carbon neutral. So they could start asking the question, well, what sort of carbon footprint could we get away with, or how negative does the concrete have to be? And if it's not clear, when we make up a yard of concrete, a normal yard of concrete has 1,200 pounds of sand, 1,800 pounds of coarse aggregate, 600 pounds of cement. 600 pounds of cement give it a carbon footprint of 600 pounds. The 1,200 pounds of normal sand doesn't have that much of a carbon footprint, but if it's Blue Planet sand, it's about negative 500 pounds. And if the coarse gravel that goes in is Blue Planet gravel, instead of 1,800 pounds of gravel, you're putting in, which has a small carbon footprint, you're putting in, about negative 700 pounds CO2. So now you have the 600 from the cement, which is, causes a carbon footprint, but now you have negative 1,200 pounds. So you have a net negative, you're net storing CO2. That's how you get to carbon negative. And by looking at things that way, it allows people to think about it quantitatively, which is what you really need. Because otherwise, someone can just fumigate, a fraction of a percent of CO2 and claim it's green and everyone's happy. And that's changing. So we're now looking at concrete more as a storage reservoir for carbon dioxide. And the reason that's significant is it's ubiquitous. So if every time people are pouring concrete, they're also sequestering CO2, you're riding the wave on the most commonly used material in the world. And that kind of changes the way engineers might think about concrete, because the way we're taught to think about concrete today is it's bad, because it has a big carbon footprint. We were up on the YouTube building with McDonough Architects, which is a well-known engineering firm, architectural firm, and the structural guy came in. He said, "This is great. I've cut the amount of concrete in half." And he'd requested very strong concrete, because he'd requested that. And we had to say to him, "No, you actually were supposed to double the amount of concrete, because the more concrete you use, the more carbon we can offset with the steel and everything else." So the whole way an architect or a structural engineer would think about the use of concrete requires that they take into consideration now that you're not necessarily, and there's other reasons you might want to minimize the concrete, but you're not necessarily just trying to get rid of concrete. In some cases, you may want to be taking advantage of something you're trying to do and increase the amount of concrete to have more carbon negativity. And that's what we're seeing in the interactions we're having. But there's a big circular component of it as well. So to make concrete, we need coarse aggregate and sand. We need cement, water. And the aggregate can come from the Blue Planet process, which I'll show you. But it does end up in concrete, which gets used, and at the end of its life, we've actually taken concrete and put it back through the process to make more aggregate. Thanks. So we're working with a broad range of sources. The differences are like from direct air capture, you get pure CO2. Cement plants are about 30% CO2. Steel varies. Refineries have a steam methane reformer that puts out purified CO2. So that we're able to capture the CO2 from a broad range of processes. Another technical point that we think is going to really change the way we manage CO2 is we don't purify it to liquid CO2. We just turn it to a bicarbonate aqueous liquid, like Perrier. That opens up a lot of avenues that aren't currently available. And just a little background, if you take a ton of CO2 and say you make mother of pearl out of it, that has a volume of 1 cubic meter. If you take a ton of CO2 and compress it into a liquid, it's about 1.1 cubic meters. If you make it into a limestone porous aggregate, it's 1.6 cubic meters. If you make it into a bicarbonate solution of various concentration, it's about 11 cubic meters. And if you make it into pure CO2 gas, it's 25 cubic meters. Or we have a plant at a natural gas-fired power plant, and we have to bring in 80 cubic meters to get 1 ton of CO2 because it's dilute. Or if you're doing direct air capture, you have to process 1.25 million cubic meters of air to get 1 ton of CO2. That's like your stadium here. what that does is, if you do what the classic method that most carbon is planned to be managed in the future is, it's called CCS, carbon capture and sequestration. You purify it, liquefy it, compress it, and move it out and inject it underground. If you compare that to what Blue Planet's doing, we send out a solution, we capture the CO2, and we send it back, and it uses about 1/40th the amount of energy to manage it that way. And this has a lot of important implications for how we're going to really manage this on a very large scale. So I'll show you. We use various raw materials. In San Francisco at our plant, we use returned and demolished concrete. We bring it in, dissolve the calcium oxide out of it. We use that, but there's a number of materials that are available, including different rock types that we use. The process itself is really pretty simple. We dissolve calcium oxide out of waste materials. We put it through an absorber. We make a calcium carbonate aggregate. We also have been able to plug into hydrogen generation as well. And instead of pulling CO2 just out of flue gas, we can pull it out of hydrogen that has come out of certain processes that is really going to make blue hydrogen much more available. But the products we make available to the concrete industry are sand, both coarse and fine sand. And then in the case, like in this case, we've used demolished concrete as our calcium source, and we're still left over with the original aggregate that was in it, which can also then be reused and recycled. The way this is going to deploy globally, like we're developing one of these in Singapore right now, is we're putting together carbon emitters, feedstock providers, off-takers of building materials, all together into one entity. And it turns out that this doesn't really increase the price of a building hardly at all, which ultimately can determine whether it's going to be adopted or not. You can increase the price of the building by 0.5% and bring the concrete to total carbon neutrality. You know, so if you ask Google, who are desperately trying to lower the carbon footprint of their data centers right now, or AWS or any of these people, is it worth 0.5% increase in the cost to be carbon neutral? And just say absolutely, you know, compared to a carbon offset or something else they need to do. So it's a very workable model. Just to kind of show the proof of it, we did a big part of Terminal 1 up at SFO, San Francisco International Airport. And they use the Carbon Star rating, you know, the one I showed you earlier. And to even bid on the concrete job at SFO, you have this one goal where the carbon footprint of the concrete has to be 200, which means 200 pounds. Now remember, there's 600 pounds of cement in there, so they're lowering the carbon footprint by 2/3 already, just a bid. And then they have what's called a reach goal, which is 0, so 0 pounds carbon footprint per cubic yard. And then they have a regenerative goal, which is negative 200 pounds per cubic yard. And if these are bids come in at the same price, the lower the Carbon Star number, the more preferred procurement it gets in the procurement process. So they're providing a quantitative means to encourage procurement of the lowest carbon materials by using the County of San Francisco's purchasing power, which is way more powerful because you can do that at any airport in the world. You know, you don't need a government to say it's okay. You know, so it's super powerful. And you know, even with private companies, there's a lot of shareholder pressure coming onto the management to do something about their carbon. And so even, companies building data centers today have this incentive to want to have a low carbon future. This is where we're at. We've been operating this plant up on San Francisco Bay for about 2 years. It's co-located with a natural gas-fired power plant that runs most of the city and county of San Francisco. It puts out over 2 million tons of CO2 a year. We're building another plant right now that's about 10 times bigger on the same site. And then at this site, this little blue square is this blue square. We're expanding further, and these are the pipelines taking the bicarbonate solution from, capturing it from the flue gas. This is the power plant. From the power plant, taking it over to our site. We also have a 10 million ton bulk handling facility. And this is the bay where 75,000 ton Panamax vessels can come up and get huge amounts of aggregate. And so we run this plant regularly, and that's where we're making the limestone right now. But there's been an enormous amount of interest. We have projects going in a number of spots around the world right now. But to end, I just want to show you the manifestation of this, because we're not just offering a new product. We're offering a whole new carbon management system that's actually scalable and sustainable and isn't dependent on subsidies from the government. The red line represents solids, like our aggregate. The blue line represents the bicarbonate solution we make after we contact our absorption solution with the CO2. And the yellow is gas, meaning it's like flue gas that would be taking CO2 into the atmosphere. So we can locate a Blue Planet plant, and we can co-locate it right next to, say, a cement plant and take the flue gas directly in. It's really hard to move gas because it's compressible, so it's easier to move liquids or solids. So you never want to do that a long way. But we can also have a plant. Remember I said we use 1/40th the amount of energy to move carbon around? This could be 100 kilometers away. And it doesn't need any special pipes that can contain high pressure or anything like that. Well, here's what that looks like. One of our investor and partners is Holcim, which is the largest cement company in the world. And same blue, red, and yellow things, for gas. So the yellow is where the CO2 is being emitted from. This is an industrial complex in France. And the blue is the bicarbonate solution going out to the CO2 sites, capturing their CO2, turning it into a bicarbonate solution. And the red represents either raw materials coming in via barge. This is a barge lane. We're going back out. And the reason it's significant is to replicate this kind of infrastructure would take decades, if at all possible, with all the permitting and all this stuff. You can do this in a few months. You can go into an industrial site and pipe it up and get going, which totally changes the way we think about it, because anything that isn't going to happen by 2030, no matter how good it is, there's a problem there. We need to be doing major mitigation by 2030. And these ports are all around the world. And what's really interesting is there's this class of ports called pre-Panama Canal ports that have a certain draft that a lot of ships can't get in. And they're starving for business. And so there are all these ports with all this infrastructure that we can literally just move into really quickly. So this rapid implementation, we think, is really important. But I better stop there.
Well, I didn't know you were Brent, the Carbon King Constantz. It's like, geez, that you really have a sustainable solution. Like maybe the best.
Yeah.
So let's give a round of applause here. Are any burning questions here? I know I got a few, but I'm probably going to save them for afterwards. You got one here?
So
Okay.
If you could return to your slide of your sand contents, I'd love to know where you'd like to get your sand from.
We make it.
Or that. And also maybe the logistics of moving sand, as that's a very large challenge in a similar industry. So,
no, we actually, at this particular plant in Pittsburgh, instead of having to fill a whole silo with sand back at a ready-mix plant, our concrete partner has a truck that comes right out to the site, and you can mix the concrete right on site. But yeah, as you know, it sounds like if you can't fill up a whole silo and use it every day, the ready-mix guys aren't that interested, because they don't have an unlimited number of silos.
The Anthropocene has us moving more earth than any other creature, so to speak. I commend you for what you're doing. It's a pretty amazing presentation. I'm sitting here pretty awestruck right now, so thank you.
Yeah, I echo that as well, like to where heard a lot of presentations on solutions, and this is one that makes sense. Knife River used to be a sponsor of mine.
Oh, really?
And so I'm, good friends with the president up there, and obviously North Dakota company. They pour a lot of concrete.
Yeah, they're an investor of ours.
Oh, okay. Oh, there we go.
Dave Barney was on our board, and now Brian Gray is our guy. He's the CEO up there.
Okay. MDU, is their parent, I guess you could say.
Yeah, they spun it off.
Yeah. But any other, questions? We got one more. Oh.
So how are you capturing the carbon at the, is the capture methodology the same as Carbon Collect is using out here in this?
Yeah, so
facility?
it depends on the CO2 concentration. I totally skipped over that to get through the presentation. But so our largest single dollar investor is a company called Sulzer. It's a Swiss
called what?
Sulzer, S-U-T-L-E-R, Z-E-L-E-R. It's a Swiss company, and they're the market leader in gas liquid contacting technology. But basically, at our plant, it's about a 40-foot column. And the flue gas goes in the bottom and goes through porous media and comes out the top. And our absorption solution, which is just aqueous ammonia, comes in the top and trickles down, and they pass each other. And that aqueous ammonia is now ammonium carbonate when it comes out the bottom. And then we have another stream of calcium chloride that comes from the dissolution of the concrete.
And that turns into aggregate?
Well, it precipitates calcium carbonate. And one of the reasons we study biomineralization is it turns out there's a whole suite of different calcium carbonates, and they have interesting properties. But it basically looks like cream or milk. It's a suspension of a precipitate. And then we dewater it, and then we have chemistry that makes it harden up into rock. It's sort of an artificial lithification process. But that's the trick.
Yeah, with your kind of mild demeanor, people may not realize how big of a solution this is. I mean, tremendous. And so my hat's off to you getting to this point, and obviously it's validated. You know exactly what you're doing. And so I'm very excited to continue this conversation, at some point in time. But yeah, let's give another round of applause here for Brent. Okay.
Good job staying awake, everybody.
No. It's there was a lot. I mean, you covered a lot there. So I'm gonna have to digest it, over time.
Well, I got up at 3 in the morning to fly down from San Jose today. So.
Well, thank you so much for doing that, and what a pleasant surprise, coming in kind of last minute too. I was like telling John we were saving a spot, and couldn't be a better fit. So thank you so much.